Hi everyone, we're going to make a presentation of our final project, AI Agents for Sequence Game. For the game rule, the goal is to score 2 points before your opponent. You earn 1 point for every 5 in a row you complete. If you occupy all 4 center positions, you instantly get 2 points. The game is partially observable and stochastic. Finally, with only 1 second allowed per move, agents must make fast and intelligent decisions.
Now let me give you the tour of our main agent. We drive it with a heuristic-guided alpha-beta search. The pipeline is simple but tight. First, immediate tactic check. We first ask, can I treat a dead card? Can I win or block right now? And if I should use jack cards? Second, we run a quick heuristic score on every legal move. Third, we keep only the top 3 candidates. Fourth, those 3 candidates go into a depth 2 alpha-beta search with the opponent limited to 3 replies. Finally, we always exit before the time limit, so the last box is return the best move and still live. Overall, this pipeline lets us look 2 plays ahead without ever timing out. So what's inside that heuristic? We use many key parameters like this. Max sequence length gets 0.6 bits, positive because extending a streak is how you score. Opponent streak length is negative 0.5. We punish states where the enemy is close to 5 in a row. Center control gets a strong 3 because if you tick all 4 central squares, that's an instant win. So owning the center is a huge tactical advantage. We give a 4 bonus when a move instantly creates 4 in a row because it sets up a forced win. Finally, jacks are special. A wild jack is 15, a remote jack is 10. They are basically tempo bombs, so they jump to the front. On the search side, we keep it shallow. That's 2, prune with those top 3 limits, and we cut off at 0.9 seconds to leave a safety margin.
Our MCTS agent follows 4 standard phases. However, due to strict time limits, we only expand root level actions. We guide selection with UCB1 plus a heuristic bias and simulate random games. Results are back-propagated to update win rates. To select an action, we apply the UCB1 formula with an extra heuristic bias term. UCB1 helps us balance exploration and exploitation, but since we don't build a full search tree, we use a progressive bias here. We assign each root action heuristic score based on its tactical value, like whether it helps form a line, blocks the opponent's 4 in a row, takes a center position, or uses specific jack cards. These scores are added to the UCB1 formula. We tune the bias weight to 0.45. Without this, our flat MCTS agent would waste time exploring obvious bad moves. In our simulation phase, we perform uniformly random simulations. Each simulation is capped at 50 half moves to respect the time limit. The rollout does not use any heuristic. Initially, we experimented with using heuristic guidance during simulation, but it introduces significant overhead. As a result, we decided to apply heuristic only during the selection phase. This allows us to preserve the integrity and speed of the simulation, ensuring that each rollout remains lightweight and consistent. The final state of a simulation is scored based on a simple reward function: 1 point for a win, half a point for a draw, and 0 for a loss. This simplified simulation strategy strikes a good balance between efficiency and reliability.
Hi everyone, now I will continue to explain how a Q-learning agent was designed to learn efficiently in a game environment with hidden information. In sequence, although the board is fully visible, we don't know the opponent's hand or the upcoming drop cost. This uncertainty makes long-term planning very difficult. To tackle this, we focus on local interaction. Instead of modeling the full game state, our agent only considers features around the move itself. At the core, every move is converted into a 7-dimensional feature vector. This feature describes whether it's a place or a move action, and so on. This way, the agent learns the impact of local moves without simulating future turns. The Q value of each move is estimated using a simple linear function of this feature. This keeps learning fast, stable, and easy to debug. Because rewards in sequence are sparse, we also added reward shaping. This gives the agent more frequent feedback on how it's discovered useful tactic early. Finally, to balance exploration and exploitation, we use an epsilon greedy strategy with decay. At the beginning, the agent explores randomly to avoid premature convergence. Then over time, epsilon decays, allowing to focus on what it has learned. Together, these design choices allow us to train a competitive agent efficiently, even under partial information. In this agent, we explore 3 AI methods. Our alpha-beta agent proved that shallow search with strong heuristic can be highly effective. The MCTS agent kept things simple with heuristic-guided UCB1 selection using bias. And our Q-learning agent learned strong strategy using early local features and shared rewards. Working together, we combine our strengths and improve our agents iteratively. It's been a valuable learning journey in both AI development and teamwork. And that's all about our project. Thank you for listening.